In 1956, a locomotive climbed Sherman Hill, Wyoming, the steepest sustained grade on America's transcontinental railroad. It hauled 4,200 tons at 22 miles per hour without slipping, without stalling, without helper engines pushing from behind. Nothing unusual about that, except for one problem: the design was Soviet. At the height of Cold War paranoia, the Union Pacific Railroad had purchased technology based on Russian articulated locomotive principles, and FBI agents were investigating whether it constituted espionage. Congressmen called it communist junk. American manufacturers refused to build it. Yet on that mountain, with federal investigators watching, this enemy machine outperformed every American locomotive that had ever attempted the grade. Some were twice its size. How did Soviet engineering solve a crisis American railroads could not fix? And what happened when the test results came in and no one could deny them? Sherman Hill wasn't just steep. It was a 1.55% grade sustained for 30 miles, a grinding mathematical certainty that destroyed schedules, finances, and faith in American engineering. Every ton of freight moving west from Omaha had to climb it. Coal for California, grain for the Pacific Fleet, steel for the post-war boom. The entire continental economy funneled through this bottleneck, and by the early 1950s, the bottleneck was winning. The Union Pacific tried everything. They built bigger locomotives, massive articulated Challengers and big boys, some weighing over 1 million pounds. More weight should mean more traction. Basic physics, right? Wrong. The rigid frames could not distribute force across curves and grades. Wheels spun uselessly. Couplers snapped under strain. Locomotives derailed on curves because their fixed wheelbases could not negotiate the geometry. In 1952 alone, Sherman Hill delays cost Union Pacific $8.3 million, equivalent to $95 million today. Communities waited days for deliveries. Perishable goods rotted in cars. The problem was adhesion. A locomotive can only pull what its driving wheels can grip, and grip depends on weight distribution. American designs concentrated mass on rigid frames, hit a curve or grade, and weight shifted unpredictably. Some wheels lifted, others bore too much load and spun. The harder engineers pushed, the worse it got. You couldn't muscle your way up Sherman Hill. You had to dance with it. But American railroads didn't dance. They doubled down on size, power, and brute force. The same orthodoxy that had built the Transcontinental Railroad. Admitting that approach had limits felt like admitting America itself had limits. So they kept building bigger engines and watching them fail. Then someone looked east. In 1932, Soviet engineers at the Leningrad Kirov plant designed the L-class, a locomotive that violated every American assumption about power and control. Instead of a single rigid frame, it split the locomotive into articulated segments. Each segment could pivot independently, following the rails through curves like vertebrae in a spine. Weight distributed dynamically. As one set of wheels climbed, others stabilized. As the locomotive curved, segments adjusted their angles, keeping every wheel pressed to the rail. American engineering journals dismissed it immediately. Too complex, too many moving parts, too foreign. The prevailing wisdom held that articulation meant weakness, that splitting a locomotive would reduce tractive effort and create maintenance nightmares. No major United States manufacturer would touch the concept. The mallet-articulated engines used in America kept the boiler rigid, articulating only the front engine. The Soviet approach, full articulation with flexible connections, seemed heretical. But desperate times breed heretical thinking. By 1955, Union Pacific executive William Jeffers faced a choice: keep losing millions on Sherman Hill, or test a concept American engineers had rejected for 2 decades. The railroad approached Fairbanks Morse, a manufacturer willing to experiment. The design they proposed used Soviet articulation principles adapted to American gauges and specifications. 3 segments. Independent bogies. Distributed weight across 18 driving wheels instead of concentrating it on a rigid 12-wheel frame. The reaction was immediate and vicious. Members of Congress demanded investigations. How could an American railroad purchase communist technology when Soviet tanks threatened Berlin? The FBI opened case file 100HQ374826 to investigate whether the design transfer constituted illegal technology sharing with an enemy state. Union Pacific engineers received threatening letters. Fairbanks Morse faced boycott threats from industrial unions. William Jeffers responded with one sentence: "I don't care if it was designed in hell. If it climbs Sherman Hill, we're using it." October 1956. Sherman Hill, Wyoming. Temperature 34 degrees Fahrenheit. Wind 22 miles per hour. Grade 1.55% for 28 miles. Observers included Union Pacific executives, Fairbanks Morse engineers, 2 FBI agents, and reporters from Railway Age magazine. The locomotive they called the Leningrad Special, officially FM Trainmaster Model 3808, sat at the base of the grade. Behind it were 4,200 tons of coal in 76 hopper cars. The equivalent American engine, a General Electric U-25B, had stalled with 3,600 tons the previous month. The massive Union Pacific Big Boy articulated 1,208,750 pounds, the largest steam locomotive ever built, had required 2 helper engines to move 4,000 tons up the same grade 3 years earlier. The test was not secret. Union Pacific wanted witnesses, because if the Soviet-derived design failed, they would bury it quietly, and if it succeeded, they needed undeniable proof. At 9:42 a.m., engineer Thomas Callahan opened the throttle. The locomotive moved smoothly. The articulated segments flexed through the initial curve, each bogie adjusting independently. Weight flowed across 18 wheels like water finding level. Wheel slip indicators, the instruments that measure the microscopic spinning that precedes loss of traction, barely flickered. The train accelerated to 15 miles per hour, then 18 miles per hour. At mile marker 12, where the grade steepened to 1.65%, Callahan pushed to 22 miles per hour. The American locomotives had stalled at that exact spot. The Leningrad Special did not hesitate. Its distributed weight meant every wheel gripped. Its articulation meant curves did not lift wheels or concentrate force destructively. The Soviet engineers had understood something American designers missed. A locomotive is not a battering ram. It is a negotiation between steel, gravity, and geometry. You do not conquer a mountain, you flow over it. At 12:17 p.m., 2 hours 35 minutes after starting, the train crested Sherman Hill. Total wheel slippage was 3.2%. Fuel consumption per ton mile was 41% lower than comparable American engines. 0 coupler failures. 0 wheel lift events. The FBI agents drove back to Denver without filing charges. The Soviet design worked because physics does not care about politics. Railway Age published the test results in January 1957. The data was unambiguous. The articulated, Soviet-derived locomotive had outperformed every American design tested on Sherman Hill in 2 decades. It hauled more tonnage, climbed faster, consumed less fuel, and demonstrated superior adhesion across curves and grades. The engineering community could not dispute the numbers, so they disputed the credit. Within 18 months, General Electric announced development of a revolutionary new locomotive with independently articulated bogies and distributed weight architecture. Alco followed with its own advanced articulation system. Electromotive Division released technical papers describing dynamic weight distribution, using the exact principles refined at the Leningrad Kirov plant 25 years earlier. None mentioned the Soviet origin. Union Pacific quietly purchased 43 additional articulated locomotives over the next decade, rebranding them as American technological leadership. Congressional critics went silent as Sherman Hill delays dropped 73% and cost per ton meal fell 38%. The same politicians who had demanded espionage investigations now praised American ingenuity for solving the mountain grade crisis. The Leningrad Special itself disappeared from official histories. Union Pacific retired it in 1968 and scrapped it 2 years later in 1970, destroying the physical evidence of where the solution came from. Modern railroad museums display American articulated locomotives with plaques celebrating American innovation in distributed power systems. Engineering textbooks credit General Electric with pioneering articulated bogie technology in the late 1950s. The Soviet contribution was erased, not because it did not work, because it worked too well. Today, virtually every modern diesel-electric locomotive uses the articulation principles refined by Soviet engineers in the 1930s. The Chinese CR400 high-speed train, the German Siemens Vectron, the American GE ES44AC hauling freight across Wyoming. All articulated, all distributing weight dynamically, all descended from the design American engineers once called communist junk. Sherman Hill still stands, a 1.55% grade, 28 miles long, unforgiving as ever. But modern locomotives climb it hauling 5,000 plus tons without slipping. Not because American engineering suddenly became superior, because American engineering finally stopped letting ideology override physics. The lesson isn't about locomotives. It's about what happens when pride becomes policy. The Union Pacific lost $8.3 million in 1 year, and countless millions more because American orthodoxy insisted bigger meant better. Soviet engineers solved the problem because they asked a different question. Not, how do we build the biggest locomotive? But, how do we keep every wheel gripping the rail? Innovation has no flag. Physics respects no ideology. The best solutions win, not because of where they come from, but because they work. And sometimes the hardest climb isn't the mountain. Admitting someone else found the path first.